There we go. Now we're recording. Okay. What I was just saying was this whole exam 2 is going to have a lot of content that gets very repetitive, and I'm going to have to say this all again, but basically it all revolves around 2 carbons. There's 1 carbon that is going to do a lot of, like it's going to act as an electrophile a lot of times, and the other carbon is going to act as a nucleophile a lot of times. And so basically the carbon that is going to be the electrophile will a lot of times form a tetrahedral intermediate, and you'll do a lot of different stuff from that tetrahedral intermediate. For aldol, it just stays as an alcohol. If you want to make a alpha beta unsaturated keto group, that the hydroxyl group will leave. For acetoacetic ester, you do all kinds of stuff. Dieckmann, Claisen, they're all using the same premise of you've got a nucleophilic carbon that is going to act in the blue. That's how I've denoted it here. And then there's another one that's going to be electrophilic, and that's the one that I've denoted with yellow. And so the yellow one is going to make the tetrahedral intermediate. The blue one is going to be like your enolate ion. And so the enolate ions have acidic hydrogens. And so from that acidic hydrogens, those hydrogens will get plucked off. And then they have a negative charge that can act as a nucleophile to form other to attack other carbons that have partial positive charges and form new carbon-carbon double bonds. And so that's like going to be kind of the pillar of the second exam. And so we're going to start off here. I just went ahead and drew like your aldol product here. So you'll notice these are just an exact duplicate of the reagent. And then you've just got your enolate ion that's going to attack the other one where there's an electrophilic site. And so the electrophilic site for this one is going to be in yellow. It'll be here on the other reagent. And so that's pretty much all there is to aldol. And for this one, actually that acidic hydrogen is going to leave and its electrons are going to fall into a double bond. And so the new carbon-carbon bond for these aldol to then alpha beta unsaturated ketones is going to be formed from like the acidic hydrogens leaving, if that makes sense. I know that's a bit of a mouthful, but bear with me. This stuff isn't necessarily on your exam, unless maybe a little bit of aldol is if you're in Nichols. But yeah, so for this next one, once again, the exact same thing where this is the second molecule. This is going to be the electrophilic site, and the nucleophilic site is going to be 1 carbon over on the enolate ion. Oh, man, people send me messages in the Canvas thing, like during recitation, about how to get into recitation. Okay, we're back to the recording thing. Yeah, for the next one, we've got an internal kind of collapser and formation of a ring. I denoted alpha and beta carbons. Dagnabbit. And oh my gosh. Okay, whatever. We'll worry about those later. Okay. And then, yeah, that's that. I've denoted the electrophilic carbons with blue, or no, not, wait, yes, with blue. And the nucleophilic carbons with blue, dagnabbit. And the electrophilic ones are yellow. Look for these trends. Same thing here. Aldol formation is going to involve like a ring. And then basically for aldol, to make an unsaturated alpha beta ketone, you've got to do just like the hydroxyl leaving. And then once again, those electrophilic, or no, the acidic hydrogens will leave and make the double bond. So that's all there is for that first section. Are there any questions about this first unit or first little part? Hey, I'm glad you got in here, Daniel.
Glad to be here.
Right on, right on. Okay. So for this next one, the next section just has perfect like duplicates, but for me, it's hard for me to like see when they look exactly the same. Like low key, this molecule and this molecule and this molecule are all the same, but to see it, it helps me to draw it in the same orientation that I see it in the product. So I start out with this because it looks most like this, and then I redraw that as this because they're actually the same. Does that make sense? Cool. Once again, nucleophilic site, electrophilic site. For the next one, it's the exact same thing. I went ahead and used highlighter to cover over which reagent belongs to which region of the product. Same deal with aldols, hydroxyl groups leaving, and then the acidic hydrogens, electrons falling into a double bond. Is there any questions here? No? Cool. All right. So for this recitation, there's one little hidden sneaky thing that shouldn't be on there, and that is that this right here has a methyl group that shouldn't be there. So pretend like it's never there, and that's for group 2, or the section 2 of problems, which will actually be designated to groups 3 and 4. So look back at your recitation 3 for specific like reagents that might help you remember some of them. And yeah, same thing we've been doing with the group assignments. Only thing that's a little bit different is this first section of part 1. So group 5 and 6 will do this first one. Oh, shoot. We'll do this first one. Groups 4 and 3 will do the second one. And then groups 1 and 2 will do this one. So at this point, everybody is left. There was an error that in my first recitation that I didn't catch in the actual recitation worksheet. So there's not supposed to be a methyl group here. This methyl group was, well, to put it on would be too complicated for you guys at this level in the course. You could technically do an acetoacetic ester stuff, and I'll talk about that when I come to that problem, but for right now, let's just pretend like it's not there. So moving on, first we're going to talk about this missing reagent problem. Really, you just need to use periodic acid. So if you remember, we can use osmium tetraoxide to do diol, add like diols, send diols across the double bond. And then you can actually do periodic acid after that to basically get the exact same product as you would do if you were to do like ozonolysis. And so really you can just do periodic acid and then count out your carbons. So 1, 2, 3, 4, 5. And so you'll have this carbon here come back and attack this site. And so I'm going to go ahead and denote the electrophilic site like I've been doing with yellow, or with blue, sorry. And the electrophilic site is going to be in yellow. So sorry, I think I said electrophilic when I should have said nucleophilic. Nucleophilic will be blue, electrophilic yellow. And so when you do that, the acidic hydrogens, when you hear acidic hydrogens, think about nucleophiles, think about adding carbon-carbon bonds. And then when you hear electrophiles, think partial positive, think about the tetrahedral intermediates, think about like the aldols. Yeah, so for this one, you're adding carbon-carbon, you're adding carbon or whatever, is going to be, so this is going to be your electrophilic site or your electrophilic carbon. This is going to be your nucleophilic carbon. So you'll notice your nucleophilic carbon is doing the attacking, and your electrophilic carbon is being attacked. And it's the partial positive of a carbonyl group. Same thing we're doing here, it's just osmium tetraoxide, or not osmium tetraoxide, sorry, ozonolysis for this this guy right there. And we actually used this as a solvent. It's just the sulfur with you know, a propyl groups on either side. And then for our attacking, so this is our electrophile or nucleophile. On our electrophile is once again partial positive. And for this is where it starts becoming very important that we're numbering our carbons. By doing that, we're able to see exactly where each carbon should be when it's placed into the ring or when the ring forms. So you'll be able to identify where they started and where they ended. The third one here is you need to add across a hydroxyl group in an anti-Markovnikov fashion across the double bond. And so to do that, we're going to use boron and borohydride with, or I guess it's not a hydride because it's not a fourth hydrogen there. Just boron with THF as a solvent. And you're going to want to use peroxide with a hydroxyl group. And so once you've done that, you're going to add a secondary alcohol that will be able to be oxidized using PCC. And so once you've done that, we can now denote the nucleophilic site and the electrophilic site in blue and yellow, like I've been doing over and over again. So you'll notice the yellow is one far away and blue is here. So it's the one that's got the acidic hydrogens. It's the one doing the electrophilic attack, or the nucleophilic attack. And so next we're going to move on to the synthesis. So these are the synthesis problems. This is, like I said, what you should pretend like isn't there. And then, so for this one, once again, bookkeeping is very important. I know I talked about how I like to kind of rearrange the carbons so that they look exactly like they're seen in the product. If that helps you, for sure do that. Just be comfortable drawing and redrawing carbons and like just compounds. That's a lot of what this test is, or at least the second test. And really the first test is helpful to be if you can do that too. It's just an important skill to have. So after this, you'll notice that basically this entire compound here is the electrophile, and it will be attacked by the nucleophile, which is this compound here. I don't think there's much else to be said there, other than the fact that this is the electrophile, or nucleophile, sorry, and it's forming a bond right here. So in other words, actually I can draw here to here, and that's what I was looking to do. Kind of was fumbling over my words to get to that point. But yeah, that's it. To do the imine formation, all we got to do is just do, like I've been saying with these, pretend like these hydrogens are eventually just going to become part of the double bond. And that'll allow you to make sure that you're always having the right amount of alkanes attached to your nitrogens when you're creating these amines or enamines or imines. Yeah. So after we've gotten to this product here, it's just a matter of quickly adding that imine. So this is the one that kind of threw people for a loop. Once again, with these, whenever you've got carbons that a carbon chain that has 2 ketones in it, you're probably going to see, at least in the second unit especially, that line of carbons is going to like zip up and form a cyclic compound of some sort. For this one, and also when you do that, it's important that you number out your carbons, because a lot of times what you'll see is it could form here or it could form outside here. So it could form on, you need to figure out which side of the ketone that you're forming your compound. And then also you have to take into effect which ketone is the one being attacked and which one is the one being, which one's doing the attacking and which one's being attacked. And so whenever you see an aldehyde, that's like a dead giveaway on the electrophile. And actually, aldehydes make better electrophiles because they have less steric hindrance. So they have hydrogen here, which isn't gonna block something from attacking like an or a nucleophile. Similar like how this guy over here has this methyl group that's protecting him from attack. That's not to say it can't happen. It can. But it depends on the product that's going to be favored. So like if I had this carbon 2 trying to attack this 5, there's only 1, 2, 3, 4. That would create a 4-carbon ring, and that's just not stable. It's not going to be favored to happen. And so when we're working these, you've just got to do that, numbering your carbons. Once you've done that and you've zipped everything up, that is this whole step here. And so that will take you to, once again, recognizing that this is the electrophilic carbon, and the nucleophilic carbon is the one that is involved in giving up its hydrogen for those electrons to fall into a double bond for the alpha beta unsaturated ketone. And that's really all there is for there. Once you've gotten to this place, you can do a Wittig, assuming that we're totally disregarding this methyl group here. And that will allow us to basically swap out the oxygen here that's on this compound for the alkane subject. And so the way I think of it is, I know people were asking about this earlier, the negative charge that is on this guy will basically, those electrons will just appear into these pi bonds in the final product. So you can think of it like that, if that helps you. But in reality, there's a butane intermediate, you've got that square. And by having all these phenyl groups, it actually perfectly like aligns it up to do just the right thing, which is replace that oxygen with a carbon. And so I'm going to also now talk about specifically this methyl addition here. So we added a methyl here, or the original worksheet had that. And to do that, really, you would want to do an acetoacetic ester synthesis type of thing. And so to do that, usually there's actually an ester here like this. But really, all you need to know is that when you've got carbon that's in between two hydroxyls, or two ketones, rather, basically that carbon is going to have very, very acidic hydrogens, because if you'll remember, we can do enolate ion formations, and this usually helps people visualize it. And then you've got like a negative charge here, and that's like fluently happening all the time. It's a resonance structure, so you've got guys on both sides of that compound that are acting as electron donators, I guess, for the pi system. And so once you have this negative charge here, it can easily swap out with just like a Br for just different alkanes. And you can create all kinds of different types of alkane synthesis and add all kinds of different types of carbon compounds from that reaction. And I included the methyl or ethyl, methyl oxide here, because that basically just helps it be more basic, and that'll help with the removal of a hydrogen here on this acidic carbon. And so that's kind of like the most complicated little thing that really kind of tripped people up in my first recitation, and honestly kind of threw me for a loop, because there is a way to do this with Grignards, but the thing about it is you're going to have to, so a lot of people ask, can you add Br? And actually, I'm going to stick on this subject because it was a prominent thing in recitation. Can I add 2 Brs here? And then once I've done that, can I just use like a lithium, something like that? And the answer is yeah, you can technically do that. It will just give you 2 different products. So one product it will give you will look like One product will look like that. The other product, oops, will look like this. And when you've done that, really the thing is like, you've just got two products there, and you're gonna have to figure out how to isolate them, which is possible, but well, it's very difficult. And honestly, maybe it's not possible. I don't really know how you would do that if you do need to do that. But anyway, I'm getting sidetracked here. That's just another way of approaching that problem. So if you did do that, that works fine. And sorry if I confused you with all my discussion of topics that we'll cover in like the next couple weeks. Yeah, so remember, aldol might be touched on in Nichols' exam. I know Baloo is not covering it. And so Baloo's exam will only cover chapters 10, 15, and 16. Hopefully you picked up on that by recitation for me talking about it. But this is the very last one. You'll notice the electrophilic site is directly in the ring. And so you'll basically, it'll become a site to make where the two rings will have like two carbons where they're overlapping. And so basically the nucleophilic carbon will be charging into the electrophilic carbonyl group to form an aldol, and then that aldol will leave, and the acidic hydrogens, so the hydrogens here, are going to fall into a double bond to make this alpha beta keto ester, or alpha beta keto group thing. I don't know if I said that right. Unsaturated alpha beta ketone. Yeah, we'll go with that one. That sounds right. And people wanted to do stuff where they added stuff with this carbon-carbon bond. If you'll notice, nothing about this carbon-carbon bond or this alkene is being touched in the final product. So you don't need to do anything there. All you need to do is sodium borohydride or lithium aluminum hydride. And so it's important that you guys remember your different reagents for reductions and oxidation. So like PCC is a softer oxidizer, whereas this bad boy right here will take stuff all the way down to, or all the way up rather, I guess, to a carboxylic acid. You've also got lithium aluminum hydride, who is a bad boy who will mess up anything and everything it touches, as long as it's just oxygen carbon bonds. It will not touch carbon carbon bonds. That includes carbon carbon double bonds. It only messes with the bonds between oxygen and carbon, and it takes all of those bonds away except for enough to keep just one alcohol. So like if it's a carboxylic acid, it'll take that acid all the way from 3 bonds associated with the oxygen to just one alcohol. Sodium borohydride is the very last one. That's just going to make a bunch of ketones or aldehydes. So it'll take carboxylic acid and all the way down to just an aldehyde. And that's all you really need to know for this one. This has been a pretty good recitation. And yeah, hopefully this helps, especially with the recitation 1, where I didn't really have enough time to really cover a lot of these minutiae. And yeah, have a great week, guys. Adios. Still recording.